Hi everybody. So in this video, we're going to look at another kind of situation that can happen when we are trying to find the volume of a solid that's created by revolving. Sometimes when we're trying to find the volume of a solid, that solid is going to end up having a hole, or sometimes we think about this as just a gap in the middle. We can think about this as being kind of like a donut. It's a solid around the outside, but there's a hole in the middle. When we have a solid with a hole in the middle, we can still use cylinders to find the volume. But because the hole in the middle is taken out, we're going to need to take away the volume of the middle of the gap from the overall volume that we get. To do that, we're going to set up two integrals, and I'm going to set up these integrals in this case with respect to x, but these can be set up with respect to x or y. What we're going to do is we're going to have the integral from whatever our x values are, a to b, of pi times our big R squared dx minus the integral from a to b of pi times our little r squared dx. And the reason I'm saying big R and little r is because big R would be the outer radius, which if I were to draw that on this picture, big R would go, if you look at this little circle here that we're revolving, from the axis of revolution all the way to the outer edge of that circle, the farthest part of that region away. And little r in this case is going to be the inner radius. Or in other words, it's the radius of the part in the middle that we're removing. So if we think about this as being the inner edge of the circle, little r would go from the axis to the little inner edge. You can imagine what this is doing is getting the volume of the whole thing and taking away the volume of the middle parts, that we just have that outer solid left over. This is going to be a very similar process to what we've seen before. Draw a really good picture, label everything, set it all up, and then go ahead and actually do the integral. So let's go ahead and try number one. For number one, it says find the volume of a solid formed by rotating the finite region. Finite region means it's completely enclosed by these graphs, y equals the square root of x minus 1 and y equals x minus 1 squared, around the x-axis. The first thing we're going to want to do here is go ahead and make a really good graph. So let's see here. So the first thing I'm going to want to do is graph this guy. Now this is going to be a square root function that is shifted to the right one space. So that graph is going to look like this. It's going to start here instead of starting at 0, 0. It's going to go like this. And then we also want to graph y equals x minus 1 squared, which is a parabola that has also been shifted to the right one space. So my vertex would be here, and my parabola would look like this. Now if I'm looking for the region enclosed by those graphs, the region I'm looking at is this little petal-shaped region right here. And we're going to revolve this around the x-axis. So I'm going to take this region, and if I draw in the reflection, what you'll see is that there is a gap here between this edge of the shape and this edge of the shape. There's kind of that empty space. So because there's a gap, we consider this a hole in the middle, and we're going to need to remove that. So in order to do this, we're still going to use our volumes equal pi r squared h formula. But in this case, we're going to have a big R and we're going to have a little r. The big R in this case would go from the axis that we're revolving around, which in this case is the x-axis, all the way to the outer edge, which is controlled by this red function. So what we would do to find our big R is we would do top minus bottom, which in this case would be the red function, square root of x minus 1, minus 0. So the big R would simplify to just square root of x minus 1. Now little r in this case would go from the axis to just the inner edge of that function, which is the blue function that we graphed. In this case, that would be top minus bottom, and I would have x minus 1 squared minus 0, our axis. So my little r would end up just being x minus 1 squared. Now when we set up these volumes, we're going to do this in two integrals, and it's very important that you do this in two integrals. So we're going to have the integral from, my yx values go from 1 to 2, and I'm going to do pi times big R squared, which in this case is square root of x minus 1. And then I'm going to have dx, because since all of my cylinders would have a little height going this way, a little tiny change in x, minus the integral from 1 to 2 of pi times my little r squared, which in this case would be x minus 1 squared squared again. Don't forget that there's two of them because the little r is this and we have to square it. Pi r squared dx again. Now from here I'm totally okay if we just type it in. The setup here is really the harder part. So I would go to math option 9, integral from 1 to 2, pi parentheses square root of x minus 1 squared dx minus math 9 integral from 1 to 2 parentheses x minus 1 squared squared again dx. And I would get that my volume is 1.371. Let's go ahead and look at another example. So in the next example, it says, find the volume of the solid of revolution formed by rotating the finite region bounded by the graphs of the square root of x and x cubed around the y-axis. So let's go ahead and sketch a great picture. The first graph is going to be the square root of x. So it's going to go through zero, 0, 1, 1. It's going to kind of curve like this. The second graph is y equals x cubed. So that's going to go like this, and it's going to curve like this. Now the region bounded by those two graphs would be this little petal-shaped region here, and this time we are revolving around the y-axis. So this tells me, because this is a vertical line, I'm going to do everything with respect to y in this problem. So everything's going to be going like this. The other half of my region is going to be over here. And you'll notice that when you color these in, there is a gap between this inner edge and this inner edge. So when we revolve this, there's going to be a missing piece in the middle. It's not solid. It's got a hole in the middle. So my volume would still be pi r squared h, but this time I'm going to have a big R and a little r because there's a hole in the middle. Big R in this case would go from the axis to the outer edge of the shape. So that would be all the way over here to the blue function. In order to figure out big R, I would just do right minus left. So I would use my blue function, which is x cubed minus my 0. Now the problem is that y equals x cubed does not have x by itself. So I'm going to need to rearrange this by cube rooting both sides. And I would use the cube root of y minus 0 as my function here, because I want everything to be in terms of y. Now little r here would be this from the axis to the inner edge, which is just the red function. So the red function here is the square root of x function. So the square root of x function also does not have x by itself. So I'm going to do a little bit of rearranging there. I'm just going to square both sides to get x by itself, and I would have y squared minus 0, which is just y squared. Now again, everything here is going to be in terms of y because we're revolving around this vertical line, the y-axis. So my volume would be done in two parts. We need two integrals. It's going to be the integral from 0 to 1 of pi times big R squared, which in this case is the cube root of y squared. And we're going to use dy because all of my cylinders would have a little tiny height in the y direction, minus the integral from 0 to 1 of pi times little r squared, which would be y squared squared dy. And at this point, I'm totally okay with you typing it in because the setup is really the hard part here. So if I were to type this in, I would have math option 9 from 0 to 1 of pi times the cube root on your calculator is in your math menu. It's the fourth option. The cube root squared minus math option 9 from 0 to 1 of pi times your x squared squared dx. And my final answer here would be 1.257. Okay, we're going to look at a couple more examples here. So, find the volume of the solid of revolution created when you are bounded by y equals the square root of x and the lines y equals 2 and x equals 0. And then you're rotating it in two different ways here. We're going to rotate it once around the line y equals negative 2. So we can see that we can use other lines besides the axes. And we're going to rotate it a second time around the line x equals 4. For both of these, a really good picture is going to be helpful. So it says we're going to take the region bounded by y equals the square root of x and the line y equals 2 and the line x equals 0. So let's go ahead and graph y equals the square root of x. Y equals the square root of x goes through 0, 0, 1, 1, 4, 2, kind of curves like this. Now the other lines here are y equals 2, which is this horizontal line, and x equals 0, which is this vertical line. So if I want the regions bounded by those three functions, it's going to be this region right here. And we're going to rotate this around a new line that's not one of our axes. It's the line y equals -2. So if I were to draw that line on my graph, the axis around which I'm rotating is all the way down here. To draw the reflection, you'll notice there's a big space between this shape and the line. So there's going to be a big space between the line and my reflection. It's going to be all the way down here. There we go. You'll notice, and I think it's pretty obvious this time, there is a huge gap in here. There's going to be a giant missing piece. So when I set up my volume, I'm going to need to have a big R and a little r because it's not solid, it's not filled in. My volume is still going to be pi r squared h, but I'm going to need a big R and I'm going to need a little r. My big R is going to go from my axis all the way to my outer edge. So to figure that out, I'm going to do top minus bottom. Now the top here is the line y equals 2. So I would do 2 minus the bottom here is the line y equals -2, which is 4. Now you'll notice this is just a number, there are no variables. What that means is that this outer edge is always 4 units away from the axis, which I think makes sense when we look at our picture. 1, 2, 3, 4. Those two lines are always 4 units apart. My little r is going to go from my axis to my inner edge. So in this case, my inner edge is going to be my function y equals the square root of x minus my bottom function would be -2. So my radius would be square root of x plus 2. Now I'm going to go ahead and set up my volume integrals. So I'm going to have the integral from 0 to 4, because that's where this region stops, of pi times big R squared. In this case, big R is 4 squared. And I'm going to use dx because all of my heights of my cylinders are going to be little tiny changes in the x direction, minus the integral from 0 to 4 of pi times little r squared, and again dx. So now at this point, I'm just going to go ahead and type that in. So I'm going to have math option 9, integral from 0 to 4 of pi times 4 squared dx minus math option 9, integral from 0 to 4 of pi times the square root of x plus 2 squared dx. And my answer here would be 58.643. Now let's take that same region. So the nice thing is we already have a pretty good graph drawn here. Let's take that same region and let's go ahead and revolve it around a different line. We're going to revolve this around the line x equals 4. So I'm going to draw my graph again because it's really important to have a visual. So 0, 0, 1, 1, it goes like that. My other line goes like this. My other line was here. So I'm revolving this region, but this time I'm going to revolve this region around a vertical line, x equals 4. Now when I do that, my revolved region is going to be over here. you'll notice that the inner edges don't touch. There's a missing piece in the middle. There's a gap. So we're going to need to do this in two pieces. My volume formula will still be pi r squared h, but I'm going to need a big R and I'm going to need a little r. Now my big R here would go from the axis of symmetry to my outer edge of my function. Because everything is going around a vertical line here, I'm going to need everything in terms of y. So my axis of symmetry is the right, and that would be 4, minus my outer function is 0, so 0. My inner r, my little r, would be from the inner edge to the axis of symmetry. So right minus left, little r would be 4, minus my inner function is this square root function. But I need to rearrange it a little bit to get it in terms of y. So I would have x equals y squared. I would just square both sides. So again, I'm still doing right minus left. It's just that this case the right is the axis minus here, and here the right is the axis minus here. Now I'm going to go ahead and set up my integrals. So my integral for my y values is going to go from 0 to 2 of pi times my big R squared dy, because all of my cylinders are going to have a little tiny height in the y direction, minus the integral from 0 to 2 of pi times my little r squared dy. I'm going to go ahead and type this in. Math option 9, 0 to 2, pi times my little r squared, minus math option 9, 0 to 2, pi times and I get 46.914. Okay, that is about it. Thank you guys so much for watching. Have a great afternoon, and I will see you for some practice tomorrow.